Hackers, let's get started. All right. Was that a meow in response? All right. Okay. Are we all on live? Excellent. Okay. We are in the depths of intercepting communications. Sorry, crypto. The camera is not following me. Let's try to get it to follow me. Oh, perfect. Can I keep up? Kind of. Okay. Awesome. We're in the depths of crypto. I think people are really diving in and finding a slightly different way of thinking than maybe you are used to. It's definitely very math heavy, probably. More, I should say, it's definitely very math heavy. It's probably more math heavy than what you're used to in a typical CS curriculum. Who here feels very math engaged, math out? All right, just one person. Everyone is math okay. Good. Okay. The crypto today, we wanted to dive in and look at a couple of specific concepts that you'll need for some of the later challenges. So we already talked about RSA. We talked about AES ECB. We talked about the block sizes and the shifting of data between blocks. We talked about Diffie-Hellman. Today, we're going to talk about kind of the remaining two concepts that we haven't dived into in live lecture, which is CBC. Let me pause the Twitch because it's screaming at me. CBC, which is we talked about briefly at the end of last Wednesday's class, but we'll dive in. And then if you have time, TLS. Okay. First, a couple administrative things. Right now, cryptography is due on Monday. It's been pointed out that Monday is also fall break.
Sunday.
Sorry. It's due Sunday at 11:59 p.m. So Sunday, it's been pointed out, is fall break, which is unfortunately placed, but I guess any time in the semester it would have been unfortunately placed. So there's who here considers that fall break starts on Saturday? All right, see, so you are.
ASU literally said it starts on Saturday.
Oh, really? All right, so we have to. All right. Anyways, fall break starts on Saturday, so Saturday and Sunday overlap with the deadline, right? And typically Saturday, Sunday is when everyone dives in and does the cryptos. Those 2 days we're going to extend, and we'll extend not into the rest of fall break because there would be a point to that. You just lose more fall break. We're going to give you until next. So we'll add Wednesday and Thursday, which is not part of fall break. So we're going to extend crypto to Wednesday and Thursday. But so that's, I guess, 4 days total. But if you're assuming that you literally vanish for fall break, so in our mind, we're giving you a 2-day extension that doesn't overlap with any ASU holidays. Okay. Aside from this, now we have a problem with the schedule because to get everything we need to get conveyed to you, we have a very tight, unyielding schedule. So what we're going to do, let me pull up the syllabus. Where is the schedule? Right now we're in crypto. These dates are backwards, but that's fine. We're going to launch access control. That's unfortunately, do you have a calendar?
The 14th through the 27th.
Yes, but no.
I think there's a calendar after macOS.
Yes. See. I'll let you launch the calendar.
Hopefully it doesn't actually launch my
calendar. It'll have your calendar. Let's just launch.
It's a guest. It's a guest account.
Oh, okay. Great. All right.
Boom.
Boom. So we are right. We were going to be due here. We're pushing the due date to here. we still have to run a nice short, like consider like a little snack module. Just a little, I don't know, a little, you know, if you ever had like a multi-course meal, they'll bring out like, I don't know, some weird little doohickey, you know, like a little pretzel or something with like, consider that. We're going to run access control as a 1 week module. You all did the Linux Luminarium. You know, all who here remembers about groups in Linux, users in Linux, file permissions in Linux, the set UID bit, the set GID bit. We're going to review all of that a little bit, maybe dive in a little bit more. Hopefully not going to be crazy, and it'll still run overlapped with cryptography, with the extended cryptography, and it'll be due on the 20th. All right. We'll send out, put out an announcement, update the syllabus. This is our best attempt to accommodate the fall break while still being able to cover everything we need to cover in class.
So basically, the assignment was going to start on Monday, and the other one was going to be due on Sunday. The one that was going to be due on Sunday is now due on Thursday, but the one that started on Monday still starts on Monday. So there's an overlap. We'll put out the date so it's very crystal clear, but there's an overlap of assignments now. But the second assignment, way easier than crypto. Like way easier than crypto.
Cool.
Yep.
You're welcome. All right. Awesome. So moving on. Hopefully this will let everyone still enjoy their fall break and go from there. As a reminder, also, how many responses to the surveys do we?
400 to 500.
Yeah, so there's 1,000 people in the class that end of the module surveys we send out end up getting a response rate of about half. This is free extra credit. Please do the surveys. It's good for us to tweak the class. For example, you know, maybe we overshot with crypto in difficulty and need to correct future years. Maybe web security should have been double its size, you know, but we won't know until people tell us in part. Okay. And just as a reminder, those surveys are add up to something like 3 or 4% extra credit, which is the equivalent of being able to, you know, miss a couple of challenges and still get an A+. Anything else we're forgetting?
That's all the administrative.
All right, that's all the administrative stuff. So let's dive in to College. All right. So if you're going, what just happened? Oh yeah, that happened. Okay. So we're going to tackle some concepts here. One is cipher block chaining. One is the padding oracles and padding in general. We're going to dig a little bit farther into padding. And then if we have time, we're going to talk about TLS and the whole kind of, well, Connor talks about the root of trust and everything in the lecture, but we'll go a little more hands-on. One thing we forgot to mention is the stream on Monday.
Yes.
So Monday is as we discussed, Monday's fall break. We will still have a stream during normal class time, like an office-hour stream instead of a class that Connor will just talk about remaining concepts, if any, in crypto, and then
it'll be totally optional. You don't have to watch it, but I'll do a deep dive on concepts that people are struggling with the most on the assignment. So that's what Monday's bonus office hours lecture thing will be.
All right. Awesome. Let's roll. Okay. We talked about AES in a ECB way mostly, and at the end of the last of the Wednesday lecture, I mentioned, okay, and then there's this cipher block chaining that solves the problem where you could see parts of the penguin despite encryption, right? So let's dive in and start looking at CBC.
Not that account.
Oh yeah, that's right, because we need.
What is
we
this?
would like internet.
Hopefully that's right. Nice, it is. Get rid of that. Okay, cool. Oh boy, now I took the camera. There we go.
Boom. We're getting very good at the camera snatches. Okay, so let's dive into cipher block chaining. Boom. Okay. All right, cipher block chaining, unlike electronic electronic code book, or like electronic code book, it's just an argument that you pass to the AES cipher in PyCryptodome or whatever AES library you have going on that or that you're using. You just pass this argument as the AES chaining or block mode of operation to whatever AES library you're using, and then you pass data on and into the object that's returned, and then the data is encrypted differently. If you look at this file compared to the AES ECB level, you will have the literally, well, there's very few changes. The first change is this instead of CBC is just ECB. And then there is this initial value guide. All right, let's talk about how CBC works on the in IPython. And we're going to import crypto. Actually, let's just do copy these guys. Set ourselves up for success. What just happened? All right. So we create a AES cipher guy. And let's actually start with ECB, just as a blast from the past, right? ECB, what do we call it? ECB, what should we call it? That's hip. ECB cipher? Cipher. Oh, how about ECBC? No, that's too confusing. Okay, so ECB cipher is a nice, simple thing. Actually, we don't even have to call it anything. I'm just going to recreate it every time for reasons that'll become apparent a little later. All right. Oh, no. God damn it. Hold on. Okay. So we have the key. We're just going to put this on its own line so I don't accidentally rerun it in the future. Then we're going to do this. Okay. This creates a new cipher dot encrypt ASDF bytes. As a reminder, we'll encrypt it, except for it needs to be the exact block boundary. So we will LJust it to 16. This justifies it with a bunch of spaces, add spaces basically to the right of the string until it is 16 bytes long, and we encrypt it. Very cool. Everyone is super excited to see this again. How do I press home on this insane keyboard? The home key? Like, you know, and home? You don't use home? You just hit left arrow all the time?
I use email.
I don't know. Okay, all right. So the ciphertext is this. The plain text, let's say, is ASDF LJust 16. And the ciphertext, we put in the plain text. And that's our ciphertext. And of course, we can also run this in decryption mode. Oh my God, this is insane. Okay, we run this in decryption mode. And the reason I'm recreating it is you can't reuse the same cipher for encryption. Decryption, for not stupid, but for reasons. We can decrypt this, and then we get our ASDF padded with spaces back. Cool. We all know this. This is ECB. It's like that Jurassic Park scene. We know it. All right, awesome. So when you encrypt multiple plaintext blocks in ECB, so if we did plaintext plus plaintext, 2 blocks, and we printed this out, clearly you get 2 blocks back. Clearly means we can test this. Here's 32 bytes instead of 16. If we split this up into 2 different blocks, they're the same. So that's the 2 halves of the ciphertext. And this is why the penguin shows through the encryption, right? Because parts of the penguin that, let's just pull up the penguin as a visual aid. Block cipher mode of operation. We go to ECB. If you encrypt the penguin, big chunks of it are just the same data. There's black color in a bitmap. And so big chunks of the output are the same as well, because it just takes those blocks, encrypts it, and AES and most ciphers are a very fixed, mapping from plaintext to ciphertext. Now, you could, tiny tangent we're going to go on to, you could define your cipher around AES ECB a little differently. You say, hey, AES's block size is 18 bytes, there's 16 bytes, but my block size is going to be 15 bytes. And instead of, when I encrypt, if my plain text would have been this, instead I justify it to 15 plus I add 1 random byte to the end. And so then when I encrypt, okay, I regret this already. So if I want to have 2 blocks, I just do this twice. Very cool. Here's plain text. So there's 1 random byte, and here's my other random byte. And then if I re-encrypt it, and then I split the ciphertexts up.
We did PT plus PT.
Oh, oops. Okay. Yeah, if I encrypt it and I split the ciphertext up, they're different because there's a random block at the end. And then I know with my custom protocol, if I then go and decrypt it, and I will do that right now. I have these random values on every block. I pop them off, and I have my 30 byte long 2 block thing. Right, very cool. All right, and now I fixed the core issue of the penguin not showing up with, or the penguin showing through the encryption, except for I haven't quite, because a random byte can have one of 256 values. And if I encrypt enough bytes of the same value, I'll still have collisions in the ciphertext, right? It won't be as clear as you see in this penguin, but there'll still be some sort of pattern shining through. And even if your eyes can't pick it up, there'll be some sort of a pattern that statistical analysis tools can pick up. And with a determined enough adversary, this can lead to negative outcomes as you try to have secret conversations, such as, at the very least, your determined adversary being able to figure out, okay, well, this block is one of 256 possible ways that someone could encode a black pixel. This block is, and slowly build up with a little more complexity, the same sort of code book that they can use to decrypt, and that you have used to decrypt the ECB run of levels. Okay, very cool. So it's not so simple to fix ECB, right? And what we typically use is a completely different block cipher mode of operation called cipher block chaining. where we do embrace this concept of adding randomness to a AES block, but if you do it in a slightly different way, right? If you observe the encryption effect, right? So let's actually get back to our this guy here. We observe the encryption effect. It takes some plain text data and the key, and it outputs a completely random set of strings, a resulting block that looks completely random to us, right? And this randomness, this block is something that an attacker cannot reason about any statistical distribution of bytes, any underlying meaning, anything without already having the key and being able to decrypt it. That's a fundamental property of correct encryption, of secure cryptography. It's called cipher block indistinguishability and or ciphertext indistinguishability. I'm sorry. And the idea is just having the ciphertext doesn't tell you anything about the originating plain text, doesn't tell you crap unless you already have the key, in which case you are equivalent to the intended recipient of the message. All right. So now a different way of saying that is we have a source of kind of secure randomness, essentially. And that is the outcome of the encryption of a block. And if you recall how we tried to secure ECB in my random attempt just now, we added some randomness to it, right? And that's what we'll do, but with a much better source of randomness, which is an entire block's random output. And the way that we secure it is by XORing it into the plain text before we encrypt. So what we do is the following. We encrypt, so we have our plain text. And let's say our plain text is actually, what were we saying before? Happy birthday. We need more. Maybe happy. We're pretty close. Maybe, I don't know, let's do 8 more.
8 more?
Yeah.
Happy birthday.
Happy birthday, students. All right. Not that you all have the same birthday. That would be hell of a coincidence, probably. At that point, we start wondering, are we dreaming? Let's look at the plain text. Okay, perfect. Then we're just going to adjust that to 32. So here's our plain text. Happy birthday, students. All right. Now, if you really want to fix ECB, oops. There we go. We're going to encrypt the first block, right? Actually, no, we don't want happy birthday, students. We want the much more approachable ASDF times 8. This is 32 bytes of identical plain text. Awesome. And now we can encrypt it. And we have the same property that we had observed. We'll do happy birthday, students, later. Don't worry. We'll wish you guys happy birthdays. All right. Here's our broken ECB. This is the penguin showing through the encryption. No good. Let's fix it, right? So we encrypt the first block. As before, for now, we are kind of getting to the point where we're fixing ECB, but not yet. So CT block 1, here it is. And then we say, okay, we don't want the second block to be encrypted to the same thing. And we don't want to mess with like, okay, now we're going to pretend that the block size is 15 and insert things that are going to be broken. We're going to do something nice and secure and things that have been proven And we're going to import stir XOR. Oh, God damn it. Where's stir XOR? From crypto utils. Util, not padding. Stir XOR. Import stir XOR. All right, we're going to import the nice string XOR. Who here remembers stir XOR fondly? Everybody? As they should. All right. So we're going to take the plain text, the second plain text block, and we're going to stir XOR it with the first ciphertext block. And, okay, what's the Emacs thing to go home?
You want to go to the front line?
Yeah.
Control A for front.
Control A.
And Control E for end.
All right. Kids these days, man. Okay. We can encrypt that because we know that ciphertext, right? We just encrypted the ciphertext, and now we can encrypt the plain text here. And Control A, okay. And then we put CT block 2 equals that, right? So what we're doing here is we're taking the plain text, we're modifying it in a way that is unpredictable to an attacker. No longer, hey, we're adding one random byte, and the attacker can say, okay, well, now there's going to be, instead of a 1-to-1 mapping, a 1 to 256 mapping. Now we're completely wrecking the ciphertext here. Stir XOR, let's just see what the output of that was. That was randomness. And thus, CT block 1 and CT block 2 are completely different. Securely completely different. All right. Now, when we, of course, decrypt CT block 1, all is good. There's our ASDF, ASDF, ASDF. If we decrypt CT block 2, we get garbage. But we can XOR that garbage with CT block 1 and recover ASDF, ASDF. Very cool. Okay, let's take a look at CBC in its standard diagram. This is kind of the standard way it is taught. Here is what happens. We'll take just a typical block. We take the plain text, we XOR it with the output with the ciphertext of the previous block. Then we encrypt that, and we have the output ciphertext of that block. Super cool. Who here thinks this is super cool? Hell yeah. All right. Very cool. Now, one problem. Let's say I am encrypting a bunch of different images of penguins or whatever, right? Or images of space, right? So let's image of space. Boom. Look at all of these things. Well, one thing that most of these images have in common is right here in the top left on the very first 16 bytes, it's all black. That, maybe not. This one, yes, right? And so far, my still homespun attempt to improve ECB does nothing for CT block 1. If I do CT block 1, if I encrypt a bunch of different images, CT block 1 is still going to have the same value. Because PT, when we encrypt the plain text for CT block 1, we just take the plain text directly, right? For later blocks, I'm kind of protecting those later blocks with the values of the blocks of the ciphertext of blocks before, and that's super cool, and that breaks up this problem with ECB. But for this block, the first block, it's still kind of just encrypted in the raw like this, right? So we need to do something, right? And the do something that we do is that we just pretend there was a ciphertext block before that. And what does, to an attacker, what does the ciphertext that they can't encrypt? It might as well be random data. So we say, okay, well, let's just do a random data CT block 0 that doesn't really exist. It's just random. We call this not ciphertext block 0, but we call this the initialization vector. Thank you. It's like IV. So we call it the initialization vector, typically IV. And you'll probably just use IV to the point where you, like me, draw a blank embarrassingly in front of the classroom. And we just do get random bytes 16. Here's our CT block 0. It's just a bunch of random bytes, right? It doesn't matter what it is as long as they're random. They have no relation to the key, no relation to any plain text. We just make one up. And when we encrypt ciphertext block 0, block 1, when we encrypt plain text block 1 into ciphertext block 1, we stir XOR the plain text, that first block, with the IV. All right. And then the CT block 2, we XOR the plain text with that previous block. And if we had a CT block 3, we would XOR the plain text of block 3 with a CT block 2. And now our ciphertext is 3 blocks. The IV, which doesn't decrypt to anything. It's just there to get XORed into the first ciphertext block. And the first ciphertext, or sorry, to be XORed during decryption into to retrieve the first plaintext block. And then the first ciphertext, and then the second ciphertext block. And if we want to decrypt it, we decrypt ciphertext block 1 by XORing it with the IV. Boom. And we decrypt ciphertext block 2, or not by XORing with the IV, I apologize. We decrypt ciphertext 1 by first decrypting it with AES, and then XORing it with the IV, right? Because the plain text that gets XORed. And when we decrypt ciphertext block 2, we first decrypt it with AES, that block, and then we XOR it with ciphertext block 1 to recover that value. And again, if we had a ciphertext block 3, we would decrypt it with our AES key, and then we would XOR it with ciphertext block 2, and so on. And that's the decryption mode. This is actually a very, I linked this from the challenge descriptions. It's a very useful diagram that really tells you exactly what's going on. And this works for any block cipher. It is agnostic of the block cipher used. It could conceivably work with many other things. You could potentially, if you're a little crazy, use RSA as a block cipher, and then do this exact thing with RSA. Probably not, I mean, not a good idea for a couple of reasons, but this box is just your block cipher, in this case, AES. All right. This scheme that I just described, of course, is AES CBC. AES mode CBC here. So if we create, and now I'm going to create the cipher. If I create AES mode CBC instead of ECB, it does a couple of things. One is it automatically generates a random IV. And that's cool. You want the random IV to be handled by professionals. Again, if the IV is not random, then all sorts of problems arise, one of which is a potential ability for attackers to fingerprint that first block for potential eavesdroppers. Another thing that happens, I mean, a lot of things are bad news, as you'll find in the challenges. All right. Now, CBC mode is not the only ciphertext, block cipher mode of operation that uses an IV. For other modes, use IVs for different things. We won't go into these modes, but there is one very cool one called the cipher block chaining. And here we go. I just said, no, sorry, that's what we're talking. No, not cipher, counter. counter mode, which is also not quite used in practice, and I'll tell you why, but it has something semi-analogous is this nonce. Actually, I'm going to read about the counter mode operation. It's actually very cool. It the way that it encrypts, here's our AES magic box. It takes basically the IV and adds the block index to it to produce a pad, a one-time pad basically for just that block, and then XORs the plain text with that into the ciphertext. What's really cool about this is that you can grab the subkey, the pad, whatever you want to call it, for any given block just by knowing its index. And because that pad, just knowing the position of any byte in a stream, you could encrypt with this 5 bytes instead of 16. Right? For example, this is going completely off the rails. I apologize. I cannot help myself. We do this CTR thing as our cipher. And then suddenly I can encrypt A. Oops. Boom. And it happily does it. I'm freed from the constraints of the block size. This is AES running in what is called stream cipher mode. Super cool stuff. Okay, but not relevant to the homework, just to be very clear. All right, let's go back to cipher blockchaining world. We have, actually, let me say one more thing about the counter. One thing that's very critical with the counter mode of operation here is this nonce. This mode's equivalent of an IV. If that nonce isn't random, then bad things can happen again. Then I could potentially XOR, what can I do? On the spot here a little bit. If the nonce isn't, that's right, then with the same key, I can recover this, the output, basically, because the only thing that determines the output of AES here isn't the plain text at all. It is just the nonce and the counter. Then I could, if the nonce is reused, and I had previously recorded a encrypted conversation and showed up at the recipient's house and, I don't know, forced the decrypted content out of them somehow, or intercepted in some other way, then I could XOR, then I'm basically in a many-time pad situation that you have done. Maybe you should add this as a challenge. Maybe not. All right. Definitely not this time. Going back to cipher blockchaining again. Every time we create this cipher, we get this random IV. And when we encrypt, ASDF times 8, again, 2 blocks of ASDF. When we encrypt here, we get 32 bytes that are different using the scheme that we just derived together with the XORing of the plain text and the previous ciphertext block. And we have the IV. You need the IV to decrypt this thing. So if we do this again, we want to decrypt something. We need to pass in, let's actually save the IV first. If we were to decrypt this thing, when we create the cipher, we need to set the IV. And then we decrypt our ciphertext, and everything is happy. If we don't pass in the IV, what's going to happen? It'll randomly generate an IV, and then we get random garbage because it XOR'd the wrong thing. Wait, why did we? Oh, no. Sorry. Yes, thank you. I missaw that. So it XOR'd the wrong thing into the first ciphertext block. The first ciphertext block is random garbage. The rest is correct. Why is the rest? why is ciphertext block 2 correct even with the wrong IV? All the previous blocks are still, the ciphertext is still the ciphertext, and you know it, and it's still correct. It's just that first block is broken. Sweet. So, lesson learned. Keep that IV on you. So now your ciphertext for 2 blocks really becomes 3 blocks long. The IV and the 2 ciphertext blocks in CBC mode. If you're sending along 1 byte at a time, this can get annoying. You have to pad that byte to 16 bytes already, and then plus you add another 16. That's annoying. Luckily, most of our communications nowadays are much larger, and so something like this is okay. As we'll see, it has other problems. All right, very cool. So basically, what the challenges do and what some libraries do when you encrypt with this is for your ciphertext, we do this, right? Cipher.encrypt. Let's recreate our cipher actually. We do cipher.encrypt. And then our ciphertext, what we really do is we prepend it with the IV. And here it is, 48 bytes long. And then when we decrypt it, we take the first block as ciphertext, as the IV, and then we take the rest as a ciphertext, and everything is great. Very cool. Any questions on cipher block chaining? All right. Now we're going to dig into one of the fatal flaws of cipher block chaining. And this is super interesting for a number of reasons. And actually now I think maybe missed an opportunity to have another cool kind of explore cool concept on the way to here. But basically, an interesting thing about cipher block chaining is that the ciphertext is completely public, right? And if I, as an attacker, can intercept this ciphertext on the way to you, so it's not just, I'm not just an eavesdropper anymore. I'm a miscreant that gets the text on, for example, you mail Connor a birthday invitation, and I intercept that birthday invitation in the mail. I'm the mailman, and I carefully tweak it, and then it goes to Connor. Well, what can I do? Well, it turns out I can do some really, really cool stuff because I have full access to mess with the ciphertext. Normally, if the ciphertext gets messed up, if even a bit changes in the ciphertext, the entire plain text gets wrecked, right? If we're in ECB mode, and in most cases in the ECB mode here, nope. Okay, if you're in ECB mode and I encrypt ASDF times 4, 1 byte of ASDF, boom, great. Now I want to also decrypt it. This is going to get a little crazy. If I decrypt that, okay, but if I decrypt this stir XORed with something, and that something is X01 left. So it's just 1 bit on the very left side, left justified by 16 with a bunch of null bytes doing the justifications. 1 byte and 15 null bytes. And we XOR that into our ciphertext and then decrypt that. One sec. Then what we get is garbage. We don't flip one bit in the plain text. We flip all, or not all the bits, but we do unpredictable random damage to the plain text. But with CBC mode, we lose this property in an interesting way. Again, let's create a cipher, because I don't remember if we messed this up anymore. And then we get the ciphertext to encrypt the SDF. And the first 8 bytes of that, 16 bytes of that ciphertext is the IV. And the IV is XORed into our plain text after AES is done. The use of the IV has nothing to do with AES itself. It doesn't benefit at all from AES's awesome properties. Why don't they encrypt the IV? Makes no sense.
You could design a scheme that does that.
Yeah, CBC on mode. All right. But the IV is just YOLO used to XOR the plain text post decryption. And again, if we decrypt this, we get normal things. But now I can start messing with the IV. And check this out. What if I XOR the IV with hex 20 multiplied by 16? Actually, let's do hex 1. Let's do our old friend. If we just use hex 1 byte justified with 15 0 bytes, right? What happens here? I make very precise corruptions to the resulting plain text. The IV got changed slightly. I XORed into the IV. And so when, let's go back to CBC. When the decryption happened, I XORed into the IV here. Here's the decryption. Took the ciphertext of block 1, decrypted it with AES, XORed with the IV, with which I had XORed a 1, which caused the plain text basically to be XORed with a 1 and returned as the plain text. So I, as an attacker, without needing to know the key, just knowing the ciphertext, XORed something into it, and then when it was decrypted by the recipient, knowing the key, I made controllable changes to the plain text. This is a disaster. And it's a disaster because I can make very controllable changes. For example, does anyone remember the ASCII value for lowercase a? 97 is the decimal. 61 is the hex value. Awesome. Good job. So hex 61. What about uppercase A? Someone's pulling up the man page. 41. Lowercase b, 62 hexadecimal. Uppercase B, 42. The lowercase letters start at hex 60 plus the index. Uppercase letters start at hex 40 plus the index. To go from one to the other, you XOR it with hex 20. So if we do hex 20 times 16 here for our XOR, we can controllably change things. For example, I just swapped the casing of all of these characters. If you're inviting Connor to your birthday party, and I carefully swap all the casing and he sees his name not capitalized, feels disrespected, and doesn't show up, that's a real world consequence of just my ability of messing with the IV. Now, here's an interesting thing. I can also mess with other parts of the ciphertext. So let's say I leave the IV intact, and I say, okay, I want to mess with the first part of the ciphertext. I take the first part of the ciphertext and I XOR it with my capital guy. Awesome. And leave the rest. Wait, it is
16.
Yeah. This is ciphertext block 1. The first 16 bytes were the IV. Second 16 bytes is ciphertext block 1. I XOR that with hex 20. And I take the ciphertext block 2 unchanged. What will happen? So I'm now here. I've XORed this guy. So now my corrupted ciphertext goes through AES. I lose control of that. It's going to be random garbage. Right here is going to be random garbage. But then here, it'll get XORed into the plain text with my modifications intact and have the same result on the plain text right here. Now, now you might say, okay, well, who cares? You just wrecked your previous ciphertext. But there's plenty of situations where that could be fine. Imagine that you encrypted to Connor an entire birthday invitation with an image, maybe an image of a penguin, probably something more birthday-like, unless you really like penguins. But I know how big the image is. Because for example, you encrypted all of these invitations. You sent it to everyone, including me. But I want to lure Connor into some nefarious place instead of your birthday. Right? Now, he trusts you because you invited him to a birthday party. You're a student. He trusts students implicitly. He fights for the students. He's the one that caused this extension for cryptography to even happen. I was going to say, well, let's just make it due on Friday instead. The Friday before. You know, it's 2 days. And he said, no, we can't. Anyways, all right. So he's on good terms with the students. Now, he gets your invitation. It says, Connor, come to my birthday party. Here's my picture of a penguin. My birthday party is at such and such and such a place at Coors 170 at this time. And I want to lure Connor, instead of Coors 170, to College Avenue Commons, where there's a completely different birthday party. I wanted to go to a different birthday party for some reason. So what do? I know, because you sent me the invitation, where in the ciphertext the address is, and corrupt the previous block to XOR that very carefully. So instead of Coors 170, it says CAVC whatever. I can do that very controllably, only corrupting the image of the penguin. So all he sees is the penguin looks weird right on the very end of the penguin. He might not even notice it if he like prints that or something, right? Or if he does, he's like, oh, that's a funny, weird thing in the penguin. Doesn't think about it a second longer. Shows up to CAVC and is at the wrong birthday party. All because I was able to not care about this block in that particular context, and I was able to care about this block. Turns out this is shockingly common. Shockingly common. Cases where there are parts of the data you don't care about. And it's worth corrupting one block to control everything. Think about comments in code, right? If you start tweaking code, you start your corruption in a place where there's a comment. You don't care about corrupting the comment. You care about corrupting the code after it, right? Cool. So that's an attack against TBC. I can tweak things very controllably. Someone on Twitch said that every day they learn more things about the terminal from me mistyping something. It is one of the best ways to learn, is to make mistakes. Okay, we have 20 minutes. I don't think we'll have time for TLS until Monday. Okay, so I can tweak things and I can get CBC mode encrypted text to decrypt to something controllable at the cost of a corrupted block. What else can I do? Well, it turns out that this ability to control the decryption of CBC is absolutely fatal to security. Now, how have I been padding my blocks? I've been padding my blocks with LJust, but no one does that, because if I have ASDF left justified by 16, and I have an actual ASDF with 12 spaces, how do I know which is which? When I decrypt the block, do I know that, hey, this was just padding, or that this is something that's part of the plain text? And we talked about this last Wednesday. We talked about the PKCS pad function, where we say ASDF, we pad it to the 16-byte cipher size, and it figures out how many bytes it needs to add to get it to the correct block size, to get it to the correct block size, and it adds that many bytes with that value. Awesome. Now, when it unpads, it looks at the last byte, makes sure that there are that many bytes of that value, and then unpads them. And I have to import unpad excellent. Now, of course, if we unpad something bogus, what's it going to do here? I mean, you might say, and again, this we touched on Wednesday, you might say there's just no padding here, but how does it know that? It just says padding is incorrect, right? Throws an exception, potentially crashes the program. And if it, even if it is a correct value, and we looked at this on Wednesday as well, but if it is a correct padding that I craft myself, I can get it to correctly unpad. Okay, so now we're onto something. Let's get to a slightly more realistic situation of encrypting and decrypting, because so far we've been padding ourselves, padding everything by ourselves right here. We're now going to pad happy birthday students using actual PKCS padding. We'll pad it to 16, the next 16-byte boundary. And then when we decrypt it, we're going to remove all this we're just going to do our normal decryption right now without any attacks. Here it is, happy birthday students. And then we had padded with 7 bytes of value 7 each. And we're going to unpad that with a maximum block size of 16, and all is good. Happy birthday, students, indeed. All right. Now, let's recall what we were able to do. We were able to mess with the value of that last block. We were able to XOR it directly. And we were able to do crazy shenanigans. So let's go back to this scenario. Okay. Wait, what? No, this scenario. Awesome. And let's say I'm a wily attacker and I XOR that ciphertext, the second to last ciphertext block, where the last ciphertext block is what has the padding. It's this guy. This is 7 bytes on the last ciphertext block. And I XOR the second to last ciphertext block with, let's start with our 01 plus times 15. We star XOR this guy. Wait, though. What just happened? Ah. Okay, we star XOR this guy. And we plus the unadulterated previous one. And we decrypt it. And we unpad that. All right. We corrupted the first block there. And then we XORed a 1 into S. This is our old attack. So instead of students, we say students, right? And, you know, we can come up with the exact correct thing here. Then instead of students says something mean. And then you think Connor's birthday wishes are not as honorable as they might be. But we can do something else. We can say, you know what? We're going to start corrupting some other stuff. We get a bunch of zeros and a 1 here. So instead of a 1 on the very left byte, the first byte of this block, we XOR a 1 into the last byte of the block. Modify the plain text, which then gets unpadded. And now we cause a padding error. All right, what can we do with this? Well, one thing that we could do is change the whole rest of the padding to remove a letter, a block, remove a byte from the ciphertext. And this is super cool. We take this, so at the end of this ciphertext, again, as a reminder, if we don't unpad, we just decrypt it. It added 7 bytes of 7. What if we tweak this so carefully that it becomes an 8? And let's go back to how much time do we have? We have 10 minutes. All right, let's just stick with this. All right, so we can tweak it so it becomes an 8. Okay. Wait, no. 7 is binary 0 in hex is hex 07, which is in binary 0000 0111. 8 is 0000 1000. So we need to XOR to go from 7 to 8. We need to XOR with 0000 1111, which is F. And we need, if we do one of these and we don't unpad, let's just confirm that it works. Awesome. We flip the 8. Let's make this carefully padded. So we need 7 of these guys. Okay, for in our XOR block. So we are doing now, 9 null bytes and 7 Fs, 0 Fs. All right, now we have this 888, but we need 8 bytes of 8. So we also need to change this exclamation point into an 8. So we do 8 null bytes plus an, whatever a exclamation point XORed with an 8 is. We XOR the exclamation point out, basically using the transitive property of XOR. Oh no. Running out of time, starting to panic. Star XOR, exclamation point with hex 08. Okay, boom. Now we have 8 8s. And now if when we unpad that, we just cut off the exclamation point. Crazy. we corrupted the padding in a controlled way by being able to control the ciphertext. And in this case, since we are operating on the last block of the ciphertext, we could have to corrupt some ciphertext to do it, some of the resulting plain text, the first block to do it. But hey, if the entire message was just one ciphertext block, we'd only be messing with the IV. We wouldn't corrupt shit. Right? All right. So that's cool. In order to do that, notice that I needed to know the last byte of the ciphertext in order to pull this off. If I didn't know it, if I thought, okay, maybe it's A, and I hit enter here, boom, error, padding is incorrect. If I guessed, I don't know, maybe it is a question mark, padding is incorrect. Now, what would I have to do if I didn't know that it was an exclamation point? I brute force it. That's correct. How many values can a byte have? 256. That's trivial. We could do it, if I had more than 5 minutes left in the class, we could do it here by hand. But of course, we wouldn't do it by hand. We would say for C in range 256, we would say unpad this. Bytes C, so we convert that into a byte. We, crap, Control O. Okay. See if I can type this in 5 minutes. Okay. Oh no. Oh my god. Okay. Okay, this is not good. Yes, this is good. Okay. Why is this? Control O. No, I hit the wrong button. All right. Control O. Don't panic. 4 minutes. No one's counting. Okay, there we go. And now we do a try loop here. Okay, Control E. And then except, exception, I don't care. Not ord byte C. Okay. And I don't like doing this, but we'll just do an else here. This is if there is no exception. Yes. Okay. And we very quickly try everything, and we can go up and should see, aha, brute force and find that byte. So what did we just do? Using our ability to mess with the ciphertext and trigger a decryption. Now, it's very important. You still need to be able to trigger this decryption. This required the key to decrypt. But just by triggering a decryption without looking at the output of that decryption, just by sniffing for this exception here, we were able to decrypt the last byte. Once we decrypt the last byte, nothing stops us from changing that 8888888 to 9999999, decrypting the second to last byte and the byte before that. And in fact, we could do the same thing on a full unpadded block, because the full unpadded block will accept out when you try to decrypt it. And when you XOR that last byte to where it's a 1, it'll unpad successfully. This is called a padding oracle, and it is an insanely fatal flaw in CBC unless CBC is used very, very carefully. And in fact, in the challenges, you'll find that not only can you decrypt stuff without having the key, just by being able to trigger and observe that exception, you can also encrypt stuff, which is super crazy. Cool. All right. I think we'll end it here. 1 minute to go. Any quick questions for us? Nope. All right. Let's keep pushing forward. We got until Thursday. Keeping in mind the overlap with access control. Please don't delay despite the extension. And we'll see you on stream on Monday if you want.
And this module's a lot of work. Definitely don't delay.
Don't delay. Goodbye, hackers.